AB Calc 2.3, day number 2. Today we're going to talk about analyzing using analytical techniques for computing limits when direct substitution gives you an indeterminate form. Okay, so we spoke about in 2.3, day number 1. Wow, I don't know why yellow's showing up there. Okay, this indeterminate form is 0 over 0. Okay, this indeterminate form tells us there's more work to do. 4 of the tools that we're going to use today, and then a 5th actually that I'm going to throw in, squeeze theorem, are going to allow us to evaluate these limits when we receive or evaluate to get an indeterminate form. So let's consider example number 1, where we'll use the factor cancel method. The example says, consider this function f of x, x squared minus 2x minus 8 over x minus 4. What happens as x approaches 4? Clearly we see that kind of mental note to the side, the numerator and the denominator will equal 0. That tells us more work to do. Okay, so what we're going to do is we're going to use a factor cancel method. Because 0 over 0 is an indeterminate form, I'm going to factor the numerator to be x minus 4 and x plus 2 over the denominator, which I cannot factor, but I can leave in this form. Now what we see here from pre-calc is that there's a hole here at x equals 4. So we're going to cancel, reducing that term. Therefore, this function, everywhere except at x equals 4, will behave like x plus 2. Thus, this limit actually equals, using now a direct substitution, 6. So the function acts like x plus 2. Well, what does that look like? That looks like this. Okay, except at x equals 4. So what we'd see is a function that looks like this. And the reason why we got this indeterminate form is because there's a hole there, right? So the function itself acts like x plus 2. So this is the function x plus 2 everywhere except at x equals 4. Okay, so we can clearly see that that limit as x approaches 4 would equal 6. That's the factor cancel method. That's a very standard method that'll be used anytime you see a polynomial that looks like it can be factored in either the numerator or denominator. Likely that's the method you want to use. Let's look at the conjugate method. Okay, example 2, let's look at the function y equals, or f of x equals, x minus 1 over the square root of x minus 1 when x gets near 1. So what that means is we're going to look at the limit as x approaches 1 of x minus 1 over square root x minus 1. Well, clearly, again, mental note, we're going to get 0 over 0. Now, I could actually factor this. I could use the factor cancel method. I might do that on the side in a minute here. But likely what I would use is this method called conjugate. Okay, so I'm going to find the radical. There it is. And I'm going to multiply top and bottom by the conjugate of the radical. Well, the conjugate of the denominator in this case. The conjugate of square root of x minus 1 is square root of x plus 1. Now, to balance the overall function, I have to multiply top and bottom by that conjugate. Okay, so what happens when you multiply conjugates? So x minus 5 times x plus 5, those are conjugates. We end up getting x squared minus 25, which means that when we use this process of FOILing, the outside and inside terms actually reduce. Now, depending on the form that it's in, 2 of the terms will reduce. Okay, so you want to be careful, but 2 of the 4 terms will reduce. And therefore, we can now evaluate this because we'll see what happens here in just a second. But the denominator turns into square root of x times square root of x, which is x, minus 1 times 1, which is 1. Now I leave the numerator as is, and typically this is how it will all kind of shake out. But then you'll see a factor that you can reduce. So we can see that the x minus 1 will reduce, which leaves us with an equivalent form for this limit as x approaches 1 of the square root of x plus 1. So I do a direct substitution now. I don't see an issue with plugging in a 1 here. And to be honest with you, the worst case is that it equals 0, but it doesn't. So I'd get the square root of 1 plus 1, which means that this limit is equal to 2. Therefore, the limit as x approaches 1 of x minus 1 over square root of x minus 1 ends up equaling 2. All right, let's move on to our third method. All right, let's look at this third method called clear fractions. Okay, so clear fractions, first of all, if I were to look at this limit and I were to plug in 4, everywhere I see an x, I get 4/5 minus 4/5, which is 0, over 4 minus 4, which is 0. So you can tell again, we got an indeterminate form, more work to do. When you see a fraction in either the numerator or denominator of a rational, okay, what you want to do is you want to clear the denominator, in this case, of the numerator. So I'm going to multiply by 5 and by x plus 1. Okay, I have to do that both denominator and numerator to keep the function balanced and not change it in any way, shape, or form. Now when I distribute in the numerator, the 5x plus 1 times x over x plus 1, the x plus 1's reduce. So I get limit as x approaches 4. That will turn into 5 times x. Okay, so let's look at that on the side. X over x plus 1 times 5x plus 1. Clearly you can see that the x plus 1's will reduce and I get 5x. In a very similar fashion, if I distribute 5 times the quantity x plus 1 times negative 4/5, I would get negative 4 times the quantity x plus 1. Okay, in the denominator, I'm not going to change anything. I'm going to leave it as x minus 4. And I'm going to bring the 5 out in front and bring the x plus 1 along with. Let's see what happens here. Okay, so rewriting our limit notation, please do that in all occasions. The numerator, if I were to simplify, would end up turning into 5x minus 4x minus 4, which turns into x minus 4. All right, now what we want to do before reevaluating, right, because here I'd get 0 over 0 again, is I'm going to reduce what I can, which in this case would be x minus 4, numerator, denominator. That then simplifies my expression to 1 over 5 times x plus 1. When I plug in a 4, I get 1 over 5 times 5. Therefore, the limit as x approaches 4 of this ugly thing, x over x plus 1 minus 4/5, that's my numerator, over x minus 4, evaluates to 1/25. Okay, that's our third method. Okay, now looking at using technology, it asks us to use the calculator to determine what happens to sine of x over x when x gets near 0. Investigate using your calculator. So what I would suggest is that in y1, you put in a sine x. And actually, for that matter, put in sine x over x. So, and then go to your table and look at values. Oh, that was not cool. Let's try that again. Okay. Look at values around 0. So, and values that are pretty close. So like negative 0.01 and negative 0.1, as well as on the other side, 0.01 and 0.1. What you're going to see, and I don't have my calculator up, but what you're going to see is that these values are going to approach a certain output. Okay, so I decided that I should probably model good behavior. And what I did was I looked at f of negative, or y of negative 0.1, which was 0.9983, and then 0.01, which was 0.99998. And then we get an error at 0. And then we get the exact same values for 0.1, or the positive inputs, and 0.01, 0.998, 3. So clearly we can see that the limit, and if you went further out, you'd be able to see it even better, but the limit as x goes to 0 of sine of x over x is equal to 1. This is a limit that you're going to want to memorize. Okay, memorize that. That's one of a few limits that are going to show up very often. Now, you could also look at it graphically. So graphically, around 0, sine of x over x kind of looks like this. Now, your calculator won't show you that hole or that discontinuity there very well, but this value is at y equals 1. Therefore, you can see it graphically as well. That's another way you could look at evaluating the limit of sine of x over x as x approaches 0. Now, what I'd like to do, I'm going to do a few laws of limits on the next slide, is I'm actually going to take you through the proof of the limit as x approaches 0 sine x over x on the last slide of today's notes. Now, it is optional, and I'm going to use the squeeze theorem. So it's an interesting theorem that I think you'd find quite fascinating, and to how it is yet another method for us to evaluate limits of indeterminate forms. Okay, so let's move on to some laws of limits. Okay, some basic laws of limits, just some ideas that you should have in your back pocket when you encounter limits that might be functions added, subtracted, multiplied, divided to some power or fractional power. So assume that the limit as x approaches a of f of x and the limit of x approaches a of g of x both exist. Following properties hold where c is a real number, m is greater than 0, and n is greater than 0 are both integers. So the sum of two limits, right? If I take the limit as x approaches a of f of x plus g of x, that's the same as evaluating the limit of each individually and then adding them together. Very similarly, for the difference property, would be the difference between the limits of those two functions at x approaches a. The constant multiple rule, limit as x approaches a of some constant times f of x, is equivalent to that constant times the limit as x approaches a of f of x. You can kind of see that there's a trend in how this works. This is very similar to many other algebraic properties that we're used to using. So let's continue. We've also got the product rule or the product law of limits. So the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit of it as x approaches a of g of x. Very similar with the quotient, provided that the limit of the denominator does not equal 0. And then you've got 6 and 7, which are very closely related. The limit as x approaches a of f of x to the nth is equal to the limit as x approaches a of f of x all to the nth power, as well as the fractional power. Limit as x approaches a of f of x to the n over mth, that's hard to say, mth power, right? Fractional exponent. You can just carry that out and perform the limit first, then take the power. Provided that f of x is greater than or equal to 0 for x near a, if m is even and n over m is reduced into lowest terms. So let's look at a few examples. Let's suppose limit as x approaches a of f of x equals 2, x approaches 3 of f of x equals 2, limit as x approaches 3 of g of x equals 5, and the limit as x approaches 3 of h of x is negative 3. So if I were to look at this first limit, what I could do is I could take the limit as x approaches 3 of f of x and add it to the limit as x approaches 3 of g of x using the sum rule from above, and then the quotient rule by taking then the limit as x approaches 3 of h of x, which of course would lead us to the following. The limit as x approaches 3 of f of x is 2. For g of x, it's 5. And for h of x, it is negative 3. So the original limit should equal negative 7 over 3. Okay, let's look at the second example. We can use the constant multiple rule, the product rule, and the subtraction rule or difference rule. So I could expand this to be 3 times the limit as x approaches 3 of f of x times the limit as x approaches 3 of g of x minus the limit as x approaches 3 of h of x. Okay, over here I could do a little work to determine what that would be. That would be 3 times the limit as x approaches 3 of f of x, which is 2, times the limit as x approaches 3 of g of x, which is 5, minus the limit as x approaches 3 of h of x, which is negative 3. The original limit should then equal 30 minus a negative 3, which would be 33. All right, let's look at the last example here. The limit as x approaches 3 of g of x cubed using the power rule should be equal to the limit as x approaches 3 of g of x quantity cubed. Limit as x approaches 3 of g of x is 5, and 5 cubed happens to be 125. Therefore, that's what our original limit would evaluate to. All right, let's take a look at the squeeze theorem. All right, here we are. We're going to take a look at the squeeze theorem. We're going to show that the limit as theta goes to 0 of sine theta over theta is actually equal to 1. Now you can see in the diagram I've drawn to the right, I'm in quadrant 1, and you can see the triangle that's enclosed by this hypotenuse of 1, this vertical side length, which is green, and then this horizontal side length create a right triangle in quadrant 1. Now, using some properties of trig and some similar triangles, if you're interested, I can talk you through it on the side. It's pretty cool. The red segment is actually equal to theta, the central angle, and the blue segment is equal to the tangent of theta. So I'm going to use this inequality to manipulate and show that the limit as theta goes to 0 of sine theta over theta is actually equal to 1. So the first thing I'm going to do is I'm going to divide everything by sine theta. Okay, dividing everything by sine theta. Okay, so what I get is 1 is less than theta over sine theta is less than, this ends up being 1 over cosine theta. Okay, so so now what, right? Because I kind of see where I want to go. I see this, let me change my color here. I see this is closely related to what I'm looking to evaluate, right? So what I'm going to do, and this is something that algebraically you need to feel comfortable with, but what would happen if, like, let's say I had 2 is less than, how about 5 is greater than 1/3? What would happen if I reciprocated everything and I said 3 and 1/2 and 1/5? What does that do to my inequalities? Well, it flips the inequality. And I'm going to do that same thing here. I'm going to reciprocate each of these. So that would be 1. That would be sine theta over theta. And this would be cosine theta. Okay, so now what? Of course, I flip my inequalities. Right, so let me rearrange this because I don't like inequalities facing that direction. So I'm going to say that's less than 1, and that's less than or greater than cosine of theta. Okay, now if this is true, then shouldn't the limit as theta goes to 0 of cosine theta be less than the limit as theta goes to 0 of sine of theta over theta, which is less than the limit as theta goes to 0 of 1. Well, what would be the limit as theta goes to 0 of cosine of theta? Well, that would be cosine of 0, which, guess what? That's 1. And what would the limit as theta goes to 0 of 1 equal? Well, there's nowhere to plug 0 in because 1 is always 1, so that's going to be 1. So this tells me, you guys, that the limit as theta goes to 0 of sine of theta over theta has to be between 1 and 1. Well, what the heck is that? Then that's pretty straightforward, right? Then by the squeeze theorem, the limit as theta goes to 0 of sine of theta over theta has to equal 1. That's the squeeze theorem. It applies in many different situations. I can show you a few examples. It's actually quite cool. Once you get the hang of it, it's pretty straightforward. So that's it. 2.3, day number 2 on evaluating limits using the 5 techniques. Reminder, the 5 techniques are factor cancel. Second one, conjugate. Third one, clear fraction. Fourth one, your calculator. And the fifth one is the squeeze theorem. All right, guys, we'll see you in the next video.